Okay, so we are currently studying linear regression, and originally yi is equal to alpha plus beta xi plus epsilon I, and alpha and beta are the true parameter, but we do not know them. And then this epsilon I is following the Gaussian distribution with the zero mean and some variance value. And so if we subtract this part from yi, which is equal to this epsilon I, and then this guy will follow this Gaussian distribution. Okay, and then so we are given n pair of xi and yi, and then if we take the square of this value, which is corresponding to epsilon I, and sum them up, and then divide it by sigma squared, and then it will follow this Gaussian chi-square distribution with the degree of freedom of an n. Okay, but in practice, this alpha and beta are unknown value, so we replace this alpha as A and beta as B. In this case, so these are approximate kind of estimate for this alpha and beta, and thus they will kind of fluctuate towards the bias that the data created. So if you remember this case, so we know the true mean value of the dice value when rolling a dice, which is a 3.5. But if we observed maybe 4 and 5 and maybe 3 and maybe 6, and then in this case, if we compute the variance, and then we first compute, so this is the true mean value, but our observation is 3, 4, 5, 6, and then we observed 4 values, and then in this case the sample mean is 4.5, so 3 minus 4.5 squared, and 4 minus 4.5 squared. So if we compute their sample variance in this manner, instead of using this true mean value, this sample mean will give a small kind of underestimated value of our variance. So that's why we divide it by n minus 1. And if you remember, by replacing the true parameter mu with the sample mean, we will reduce 1 degree of freedom from the original chi-square distribution. Okay, so the sample mean is fluctuated based on our observation that we have, and in this case, this alpha is replaced with this approximate value, and beta is also approximated with this estimate of this beta value, and so we have two parts that can fluctuate towards our data. So we now have the degree of freedom less than the original number by 2. Okay, so if we had an n number of data item, and then the degree of freedom will be n minus 2. If we replace this alpha with the A and beta with the B. Okay, let's see. So it was in the previous slides, I believe. Let's see. So just to explicitly write it, yi and minus a and bxi squared divided by sigma squared. So this one will follow the chi-square distribution with the degree of freedom of n minus 2. Okay, so this is the point in this slide. Okay, and then so we obtained the estimator for A and B by using the least squares, the principle of the least square, which means we first, let's see, yep. So we first set up, this measure called a, what is that? Sum of squares of our error, and then we try to minimize it, and then that's how we obtained these two equations and our estimator for A and B. Okay, so this was our objective function, or this is how we obtained the estimator of an A and B by minimizing the error between y and a plus bxi, right? And then square it, and then we just sum them up, and then we try to minimize it, and that's how we obtained A and B. Okay, so this was called a least squares solution. Okay, because we have a square term, and then we want to have a least amount of the value in this error, and so that's why we call it as a least squares solution. But also, interestingly, the same solution for this estimator of A and B, or alpha and beta, can be obtained, or the solution is exactly the same as the solution when we apply this maximum likelihood estimator. So what is the maximum likelihood estimator? So we have some unknown parameter that will specify our distribution, and then we compute the joint probability density or probability value of observing our set of observations, right? And so we still use this particular distribution, or this this fact. And so we first think of this epsilon I, which follows this Gaussian distribution. And so the first item of, so yi minus alpha a minus beta xi, and then this one will be our epsilon I exactly. And so if we form this formula, and then this one will be the density function value for this particular epsilon I value, okay, because epsilon I is following the Gaussian with the zero mean, because the entire part of this is epsilon I, so we have nothing to subtract from from this. And then also we have sigma squared, and so the sigma is applied here, right? This is just a definition of Gaussian density function. And then we have in total n number of observations, and so we observe them simultaneously all together, and so the density value should be multiplied together, right? And so this product, or the multiplication, is converted into the summation inside of this exponent, and so it can be represented in this form, right? Okay, so this part is just a constant, and so we want to maximize this value, and that's how we obtain this alpha and beta parameter estimator. And so this one should be maximized, and then this E is greater than 1, and so this part should also be maximized, because this exponential function is just a monotonically increasing function. So the total value is maximized, and then the inside of this exponent should be also maximized, because this function of an e to the power of x, it will be just a monotonically increasing, and thus this part should be maximized, and then we have a minus here, and so this part should be minimized. Okay, and then this guy is just a constant, so we can just ignore them, and then we now have this part, okay, to be minimized based on the maximum likelihood estimation principle. And then this one will be the same as our same as our least squares formula, right? Okay, so we can easily see that this least square solution is the same as this maximum likelihood estimation. Okay, and then we will, in the remaining part of our lecture today, we will go through some formula and some notations. Okay. So the first one is these sample variance and the covariance terms. Okay, so so we can just define the variance of a y by using this sample mean, and the variance of an x by using this sample mean of an x, and then similarly this guy is sample covariance between x and y, right? So far so good, right? And then all of them, or each of them, can be rewritten in this manner, right? So for example, in this case, for this cross terms, like this term, for example, x bar times yi, and then this guy can be factored out, and then this guy, this will be equal to this, and then this guy will be y, right? And so the product of this sample means of an x and y's. Okay, and then this cross term will also be the same. And then we also have this part. Okay, so altogether, we will obtain this guy. Oh, yeah. So in this case, it will be n times sample mean of an y, right? Okay, so these are the ones that we already studied. Okay, and then let's go back and look at the definition or the formula of the estimator of B and A. So we typically represent this estimator of an A in this manner, but in this case of B, which represents the estimator of our slope, okay, so that was represented see. Yep, so this was our final formula that we obtained as an estimator for B. Okay, and then this part is exactly the same as SXX. And then this part will be SXY, which are our sample covariance and sample variance of an X. Okay, so we obtained this, which is basically the ratio between the covariance between X and Y and the variance of an X. So that will be obtained as our estimator for the slope parameter beta. Okay, and then we by using them, we can also represent this guy. Yeah, this guy is also used in several other places in the later lectures. And what was it? SSR? So what was the full name of this SSR? What was the full name of this? sum of squares of what? Residuals, right? And then what was that? So that was the measure that we wanted to minimize. So which was like I going from n1 to n and yi minus a minus b xi squared. So the total error measure, which is a sum of squares of residuals. So we called this error as a residual, right? And then if we go back to this original lecture, then yeah, what was our residual corresponding to the ith data point? So this one was something like this. If we use this blue line, okay, and then this one, no, yeah. So yeah, we have the data point here. So the error should be like this. So we have data point here, and so the error should be around this much, right? And so the squared values of these, and then sum them up. So they are called squares of, yeah, sum of squares of residuals. So each green line is called a residual, okay? The remaining part, right? So these are the error term. Okay, so this was our definition of this SSR. Okay, then let's just plug in this A and B by using these equations, okay? So A was this, right? So I just plugged in this A with this guy, and then we have B here, the ratio between the covariance and the variance of an X. Okay, then S XX S XY times XI. So these are squared and, yeah, added together. Okay. Okay, so yeah, by plugging them in, we have like 4 different terms, which seem to be quite difficult to compute or, yeah, evaluate this squared expression. But in this case, oops, yeah. So let's plug this B as well. And what was B? So this guy is B. So SXX, SXY. So this was B and X bar, right? And then from here, yeah, we can see X bar and Y bar. So inside of this parenthesis, we can do some centering, which is yi minus y bar. So we have this term, and then minus sxx sxy, which is again the b value or estimator of b or beta, and then xi minus x bar. Okay, so far so good, right? So it's nothing but just a centered version of x and y. So like if we had maybe some point around here, what will be our sample mean of an x? It will be somewhere here, right? And then the mean of y will be somewhere around here. So it's like moving this origin to this point. Okay, so these, yeah, after doing so, we now have this new values corresponding to yi and xi. So these are just the centered one. Okay, and after then, what we can do from here is that, yeah, we can do this kind of thing. So first of all, this guy will be squared, and then add it together, and then that will be S y y, right? Because this is just a sample variance of on y, right? And then what about this? This one will be minus plus sxx sxy squared times sxx, right? Because this one will be sxx. And then we have minus 2 times sxx sxy. And then what? What will be the notation put here? It is still S of x and y, which are the covariance term, because these are the result of this cross term between these two, right? Okay, and then we have one term here, and then interestingly this guy and this guy. Let's just remove it and then take the square of it, because they are the same thing. And then this is the squared, and so we have square here and then square here, but they are also cancelled out, right? And then this part and this part will be the same, right? So at the end we will obtain like sxy squared divided by sxx, right? Because these two terms are the same. Okay, and then finally we just rewrite it in this manner, right? Sxx y minus sxy squared. Okay, so that way we can derive this equation. So these are x and x. Okay, so the book doesn't have the proof for this, but we can easily derive this guy. Okay, I cannot give an intuitive understanding about the meaning of this this SSR represented in this manner, but anyways, it will be used a few more times in the later parts of our lecture. Okay, now we are changing a little bit of our topic to this, the test or the hypothesis testing on beta and alpha. Okay, so we want to do some testing on these two alpha and beta value. Okay, and then here, these are the ones that we already know, but let's look at these representations. Okay, so it is saying that, so at least we know A and B are the functions of our random variable, or the functions of our epsilons or yi's that contains our epsilon i's. Okay, and then what kind of random variable will this A and B be? So that is our question. Okay, then so these are so divided by squared, sigma squared. We already know this is following the chi-square distribution with the degree of freedom of an n-2, and then this is the equation that we just derived in the maybe two or so slides ago. Okay, and then by using all these values, like these covariance and the variance terms and SSR and so on, we can represent yeah, we can perform the testing on this beta. Okay, so let me first describe the problem setting. So here the problem setting is, so we consider this a linear regression kind of form, but we are interested in determining whether beta, which is our slope, is actually 0 or not. So our two hypotheses is as follows. So the first one is beta is 0, and the second one is beta is not 0. And what is the meaning of these two? So suppose this guy is the height, and this guy is some weight of a person. And then do you think beta is 0 or not? So definitely if weight increases, and then height will also increase, right? It may not always be the true, but there will be some correlation or some meaningful relationship between these two. So in that case, it will correspond to this. But what about this? So we still consider height as y, and then this guy as maybe, let's see, I'm not sure, but the number of hairs, okay, the count of our hairs. So it's a little bit weird example, but I try to pick up or choose some quantitative measure instead of just a blood type or maybe the location of residence or something like that, because in that case they are categorical variable. In this case, it's still a numerical variable. But But anyways, we can see that we can kind of expect that this number of hairs of a particular person is not actually related, or it's not influencing a person's height, right? So they are just two unrelated variables. So in this case, even if we do this, even if we try to do this linear regression and then try to obtain the estimate of the beta and the alpha and beta, those values will not be meaningful ones. So because first of all, this kind of equation doesn't make sense at all from the beginning, right? So this hypothesis testing is trying to answer whether the effect or whether this y is influenced by different values of an x. So that is the meaning of the first, or our null hypothesis in this scenario. And then the second hypothesis is the opposite case. Okay, and then this complicated kind of a measure. This book is saying that this kind of a statistic, okay, is actually following the normal distribution with the mean and the standard Gaussian distribution. And let's try to understand why. In this case, so we are interested in B, and so in order to do some testing on beta, not B, we will use this B, which is an estimator of beta. And then, first of all, let me ask this question. So suppose we have this statistic, and then let's consider its expectation value. So let's just ignore this part, okay? And then, what is the expectation of this? What is the expectation of this? It is 0. And why? We studied about it because this expectation of B is actually the same as beta, which is our true parameter. And we called it as an kind of unbiased estimator, right? And here beta is just a fixed, although it's unknown value, but beta is not a random variable. So that is just a fixed constant, but only this B will change and B will be our random variable, and thus yeah, we have some scaling part, but in this case we can represent it as like this, because this one will be just a constant, and then we know this guy is the same as beta, and it will be 0, right? And then can we know, can we know the variance of B, or alternatively expectation of B minus beta, okay, beta squared, okay? So this is the definition of the variance, because if x is following, if x has the true mean value of mu, and then this guy was the same as variance of x, right? So they are actually the same equation. Okay, and then about this variance of B, which is represented in this manner, and then it was actually the variance of our estimator, right? So as we studied, if this one gets a small, and then it will be good, but if this one gets large, and then our estimator will fluctuate a lot, so it is not a good situation. And then the standard deviation of this variance of our estimator, what was it called? It had a special name. Standard what? In the context of an estimator. So what was the name of this standard deviation of variance of our estimator, B? Standard error, right? So this is the value that we have to expect. I mean, this is the amount of an error that we have to expect on average when using it as the estimator for some unknown true parameter. So if beta will be, if beta was 3, and if the standard error of our estimator was 1, for example, and then you should expect that your estimator B is something like 2 or 4 and so on, right, on average. So it will have the difference as 1 from the true value. So that was the meaning of this standard error, but this one was just nothing but the standard deviation of your estimator. Okay, then I believe we derived the variance of B, right? So let me just find. So overall in this chapter we derived this expression for B and A, and then looking at considering these estimator, we considered their expectation and also the variance, right? Okay, and then altogether the variance of B, which is again the slope estimator, is represented in this manner. Oops. Right? So this is our variance of B. Okay, so now we have, B is a function of a random variable, right? And then B is also a random variable because it's a function of random variable, and also it will have some distribution, accordingly. And then at least we already, we obtained what the expectation of B and the variance of this B. So we at least have these two clues about the distribution of B. And a particular distribution that this B is following, so that turns out to be what? A Gaussian distribution. Okay, so this is just a typical story, right? And then if we know the mean and the variance, and then we have the full information about their distribution, right? And then yeah, we can do some testing based on that. And then so keep this in mind. Okay, keeping that in mind, let's go back here. Okay, so we have this, and now this guy is represented as SXX, right? Yeah, sigma squared over SXX. So this is our variance, and then this is nothing but the standardization with respect to its standard deviation and its mean. Okay, so it's quite simple. And then after this standardization, this guy will just follow Gaussian standard Gaussian distribution. Okay, and then let's just check why this B is should follow the Gaussian distribution. Okay, so that is the only one missing part. Okay, and then let's look at why. Okay, so this is our B. So in this expression, so we see xi and n and x bar and yi in this expression. What is the random variable? Yeah, only this yi is the random variable. So if you remember, xi's are all given and they are fixed value, and we do not consider them as a random variable. The only random variable is this ei's, right? Alpha and beta are also just a parameter value that are just a fixed value, although they are not known, right? And this yi, because it's containing this epsilon I, so that's why this one is a random variable, right? And then this one has the mean as this value, and the variance as the sigma squared when this epsilon I was following this distribution, right? Okay, and then all the remaining part, although they look quite complicated, they are not random variable. They are just constant when computing this. And so, yep, so like all these parts, you can consider it as a kind of constant, although yeah, this one should be multiplied and then added together. But yeah, all the remaining parts are just constant, and then it's basically a summation of yi's, right? And yi are Gaussian distribution, having this mean and the variance, right? And then altogether, we have some linear combination of Gaussian random variable, right? Okay, and then we know that the scaled version of the Gaussian, for example, you have z, and then maybe 3z or maybe 0.5z. They are all Gaussian random variable, right? Yeah, so let me ask just a silly question. Is this a standard Gaussian random variable or not? Again, is 0.5z Gaussian distribution a standard Gaussian distribution or not? Is it standard Gaussian or not? So is this Gaussian? It is Gaussian because a scaled version of the Gaussian is also a Gaussian. Okay, and then if C was following 0, 1 squared, and then the mean, the scaled version of this standard Gaussian will have the mean as 0, but the standard variance or the standard deviation will be reduced by half or half squared, right? And so this one will no longer be a standard Gaussian. It's just an obvious question, right? But anyways, yeah, this guy, this is Gaussian. And then let me ask this question. So in this case, you can view it like, so maybe 0.3y1 for example, minus 5y2. So this is just one simple example as of this equation, because this is a summation of yi, but it has some constant term associated with it. Then if we have just the two yi's, or y1 and y2, and then they will be represented in this manner. Okay, I just gave some particular coefficient associated with the y1 and y2. And in this case, okay, in this case, y1 and y2, are they Gaussian? Are they Gaussian? Right? Gaussian. And then what will their mean be? Is the mean value 0 or not? It is not, right? I keep asking a silly question. And are those two means different or the same? Different or the same? Different. The same? Okay. Different. So their mean is the different, and their mean are the same. Okay, their mean will be different because this one will have the mean as what? This guy, alpha plus beta x1 and alpha plus beta x2, and x1 and x2 will be in general different values, right? And so the mean will be different. And what about the standard deviation or the variance? Are they the same or not? They are the same as just the sigma squared, which was coming from here, right? Epsilon i's variance. Okay, and then let's just consider the scaled version of them. And then in general, if it had a 3yi, and then the variance will be like 9 sigma squared, and then this guy will be minus 25 squared as a variance, right? And then now we have two Gaussian distributions that have different means and different variance values. In these cases, if we add them together, are they still Gaussian? Are they still Gaussian or not? It is Gaussian. It is Gaussian. It is Gaussian. And that was the property, the special property of Gaussian distribution. So we have two Gaussian distributions that have their own means and the variance values. And then if we sum them up, and then they will, of course, be a Gaussian distribution. Okay, and then, so in this case, what will be the variance of y1, 3y1 minus 5y2? So again, we have Gaussian and the mean value and this variance. What will be our variance? What is the scalar multiple in this place? So yeah, I'm just reviewing what we learned in this class. So we have, it's more exactly, it's a 3y1 and minus 5y2. And then it has this 9 sigma squared and 25 sigma squared. Okay, and then the variance of this guy will be what? Can anyone give the number? Yeah, great. 34. Right. And then why is it 34? We need one additional assumption that y1 and y2 are independent, right? Okay, great. Yeah. But anyways, back to our main story. B is something like this equation. Okay, it's just a linear combination of some Gaussian variables, random variables, and then there some will also be a Gaussian, right? And then we know their mean and the variance value, and then we now have a full information about the distribution of B, which is Gaussian, and we also computed the mean and the variance, although it looked a little bit complicated, but yeah. Okay, so now we can understand this entire expression. Okay, so it's just nothing but the standardization of the original Gaussian random variable B. Okay, and then the next story is just the same as when we did, when we moved from this Gaussian distribution to the T distribution. So in practice, we do not know the sigma squared, right? And so we represent, we use this guy, okay? So what was this guy? So this guy was yi minus a minus bxi squared, right? And so, we had a 2 less, the degree of freedom as n minus 2, and if we divide it by sigma squared, and then it will follow this chi-square distribution, right? And then what? What was the role of this chi-square distribution? So this one provided some of our estimate of our variance, right? And so okay, so see. Okay, so from here we just move this guy to the top, okay, or the numerator, and that way we see those two coming from the denominator. And then what about this numerator? So this numerator is this part of chi-square distribution with the degree of freedom of an n minus 2 divided by n minus 2. So this is exactly the form of T distribution, right? Okay, and then the good thing about using or forming this T random variable was because we can cancel them out usually, right? And so they are all gone, right? So this unknown parameter is no longer exists. Okay, and then this same thing happens in this case as well. And so if we manipulate this, and then it will follow this T distribution with the degree of freedom of n minus 2. Okay, so this is our statistic that we use to perform the testing on this hypothesis. Okay, and then if we, in this case, we have to perform the two-sided testing, right? So we need what? Some significance level. So here, instead of using alpha, because we are using this alpha already in our true parameter of alpha plus beta xi, so we now use different significance level notation as gamma, okay? And then if this value is like greater than T of gamma over 2, when the degree of freedom was n minus 2, if this value is exceeding, I mean the absolute value is exceeding this threshold value, and that's when we reject the null hypothesis. Okay, and then here it is a little bit different from this equation, right? But it's quite trivial. So we have to have the absolute operator here, absolute value operator, and then all these parts are the positive value. And then what about beta here? What about beta? So beta should be replaced with the value of 0. And why? Our testing is always performed assuming that the null hypothesis is true, right? And so we have to plug in this beta value as 0. And so we put 0 here, and then only put this absolute value sign on this b. And so we obtain this statistic, okay, as a final one. Okay, any questions so far? And then similarly, in the case of an estimator of our beta, okay, and then we can obtain this kind of confidence interval, okay, when we have this significance level or confidence level. Okay, so that was for chapter 16. And let's move to chapter 17. And it's just a continuation in this regression chapter. And in this slide, we focus on testing with this alpha value. So the overall story is exactly the same. Okay, so in order to test whether this alpha was 0 or not, okay, whether this alpha was 0 or not, or alpha could be set as some different value, like alpha was maybe 3. So this is our null hypothesis, and the alternative hypothesis was like alpha was not equal to 3. Okay, so we can freely set up our hypothesis, right? Okay, and in this case, so as you can see, this statistic has this a minus alpha, and this one is making the entire statistic, I mean the mean of this entire representation, or expectation of this entire representation as what? The expectation of this will be what? Expectation? Okay, then let me ask this question. What was the expectation of A? When viewing it as a estimator for alpha, what was alpha, right? What was alpha? So this was also an unbiased estimator, right? And so altogether, the expectation will be 0 by subtracting this alpha from A, right? And then as you can see, where is this guy coming from? That would correspond to the variance or the standard deviation of our estimator A, right? And then let's go back to our, so this is something that we didn't prove, but if you remember this lecture, we studied the expectation value of B and the variance of B, and similarly we studied this expectation of an A and then variance of an A, although we didn't prove that, which was left as an exercise for you guys. But anyways, although it looks quite complicated, but we kind of analyzed or kind of did some thought experiments about why this one should make sense, right? But anyways, our A has the variance as this guy. And then altogether, if we take the square root of it and then divide it by like A minus alpha, and then we are doing some kind of standardization of making zero mean and unit variance, or the standard deviation or the variance as 1. Right? And then let's just compare if this one was shown in our lecture slide. Oop, yeah, it looks a little bit complicated, right? And it looks a little bit different from, let's see, yeah, this expression. But we can easily manipulate and prove that this guy is the same as this guy, right? Yeah. So this one is now represented as SXX, yeah, right? And then, yeah, it may be a little bit difficult to go from here to here, but instead we can, represent this guy and then plug this SSR, which we obtained. Okay, what was it? It was something like SXX, and then what? SX. Was it squared or not? It was like this one and SXY squared. Was it true? I'm just guessing. But yeah, you should be able to see the formula that we derived. But yeah, you can just plug them in, and then I think you should be able to easily prove this part will be the same as this variance. And then now, exactly the same story goes here. And then the remaining part, in this case, is to check whether A is Gaussian distribution or not, or the normal distribution or not, right? And then if we know the mean and the variance, and then we have full information. Okay, then let's see. So A was y bar minus b and x bar. So this was our formula for A. And the intent of this A, which was our y-intercept. Okay, so y-intercept. So that was trying to, or that was making our regression line. So we have here as our point, and then we have a center point with respect to x and y. So in this case, our regression line of a plus b xi, okay, so this line should always pass through this center point, right? Because in this case, suppose y was set as this guy that we had here, and then if we plug this guy as x bar and this guy as y, so we had a yi here and y bar, okay, and then it will be trivially become 0. Okay, so you can think of this process as first determining the slope, and then adjust our y-intercepts so that this center point should always pass through our regression line. Okay. Okay, and then let's look at this form. And then here, we have to check whether this A is following the Gaussian random variable or not. So in this case, this is a constant, right? And then what about B? Is this random variable or not? It is, right? So B is a function of random variable, and we further found that B is Gaussian. So this is a normal distribution, normal random variable. Okay, So it's a scaled random variable. I mean scaled version of our normal random variable, right? So far so good. And then what about y bar? Is this random variable or not? Y bar are the, as you know, the mean value or the sample mean, kind of sample mean of our observations of y. Are these random variable or not? Y bar is a random variable. Y bar is not a random variable. Okay, so it is random variable because it contains epsilon i's, right? So it will have some alpha and xi's and beta, but also it will contain basically the summation of ei's, right? Okay, and then this guy is actually the sum of the Gaussian random variable, which was our ei, and then sum of the Gaussian will also be a Gaussian. So altogether, this is Gaussian, and this is Gaussian, and then altogether the entire A will also be a Gaussian. Okay. Okay, so yep. So this guy, you can now understand that this measure is a Gaussian, and then we can do some testing, and also we can obtain or compute some confidence interval in order to obtain the interval estimate of our alpha value, right? So we typically see alpha A, which is our kind of obtained computed statistic plus minus some value, and okay, so so this was about hypothesis testing and also the confidence interval regarding another y-intercept estimator of an A. Okay, and then the remaining part is a relatively hopefully a little bit easy and hopefully a little bit more interesting than before. But here we now study this coefficient of determination in our linear regression, and it's sometimes called R squared. Okay, it has a special name or special notation as R squared. So you may be able to see R squared in many other kind of subjects or many other examples and so on. Anyways, so this is our sum of residual, sum of squares of our residual, and then we consider this SYY or the variance, sample variance of y. So in this case, it's like just a yi minus just y bar squared, right? So which one do you think is bigger between these two? The left one or the right one? The answer is this left one is bigger. And let's just draw these errors in our 2D plane. So we have these 2D plane, and then suppose we have those points around here. And then it looks like we have this kind of regression line, for example. And then you now understand our SSR, sum of squares of residual, is just a squared sum of these lengths, right? You know that, right? But what about this? So it is something like this. So y bar is somewhere around here. And then you can view it as this flat kind of linear regression line, which we do not allow any kind of a non-zero slope, right? So this is represented as y bar. And then what about the error? What about the error? Error will be like bigger, right? Bigger than this line, right? So this line will follow much more closely to our data point. Okay, so this guy is much bigger value. And then, yeah, this value is not just bigger than this one, but also this guy can be kind of represented mathematically if we do some derivation, and then this guy is represented as the summation of the two terms or two parts, where the first part is this guy, and then the other part is some kind of other part. Okay, although we do not discuss in detail about that, what that part is. Okay, and so it's like this. So it was something like 85. So this is just a sum of squares of this difference of y value and the sample mean value of y. And then suppose this value was maybe 70. Okay, just 70. It's just an example. And then you can think of it as 85 being decomposed into 70 plus 15. And then this guy is SSR. And this guy is has some other special name. Okay, but anyways, the point is this total variance that y has, okay, SYY, can be decomposed into two meaningful parts. And if we take the ratio between this guy and this guy, for example, 85, 70 over 85. Okay, so that is, you can understand this as the ratio, or the amount of your data that you can explain by using the linear regression line. Okay, so again, if we do not allow the linear regression and then we only allow a constant value, okay, and then there are much larger variances, right? And that is our total amount of a variation or variance, and then that is decomposed into this error. This error, let's see. Error with respect to this linear regression line, and then the other parts. Okay, let me just ask what that other part is. So for example, suppose, consider this point, and then this point will have this amount of an error, right? With respect to our linear regression line. But if we use this constant y bar, and then the error will be something like this. So you can easily see that this length is divided into this and this, right? You can think of this value, and the sum of all these values, square the sum of all these values as this guy, okay, residuals, sum of squares of our residual, and this part is something like 15. Okay, so that is some kind of explained part by our linear regression, and also this residual part is still the remaining part even after that our linear regression cannot explain. Okay, so this is the remaining amount even after we try to explain maximally our data. So the maximal kind of amount of data that we can explain using our linear regression is 70. And then even after using linear regression, there are still some remaining part, okay, that we can still not explain by our linear regression line, and that is this 15, the amount of 15. Okay, so this total variance of y is always decomposed into these two parts, and then taking the ratio between these two, this one is called r squared. And you can think of it, this guy is always ranging between 0 and 1. 0 and 1. And then if it was like for example, 90%, for example, and then your linear regression explained successfully 90% of your data, and then only the 10% of your data was not explained. Okay? So when saying that, what is the total amount of error or total amount of total amount that we have to explain? So that is this SYY. Okay? So this is kind of a high-level story when discussing this coefficient of determination or R squared. Okay, so intuitively, if your data is really following this straight line, and then in this case, R squared will be close to 1, which is almost a perfect case, right? But if your data is really like having no clear kind of linear kind of trend, in that case, R squared will be close to 0. Okay. And then you guys remember that quite similar kind of ideas was also, we also studied the quite similar idea when discussing correlation coefficient, right? So the correlation coefficient is something that we already studied. Okay, so let's look at the definition of R squared. So it's like SYY minus this sum of squares of residual divided by this total variance of y, and then it can be represented in this manner as well. Okay. Yeah. Then you can easily follow this example. It's just nothing but just plugging these values into this formula, and then in terms of the relation to the correlation coefficient, our correlation coefficient R was represented in this manner, right? So we have some covariance part, and then this standard deviation of x and y, right? And then we now have some convenient notation in this chapter, which was the covariance term represented by this, and then the standard deviation can be represented, or the variance can be represented by this, right? Okay, and then we had this formula that we derived in the previous slide, and then this R, what was it? So this was correlation coefficient, and then let's just take the square of it, and then this R squared is not R squared. Okay, so this is just the squared value of correlation coefficient. And in this case, it will be squared in this manner, and it can be represented in this manner because in this case, it can be moved to the other side, and then this value is represented by this guy minus this guy, and that's why we have this numerator. And thus, if we follow this derivation, and then you can see that this squared value of correlation coefficient will be the same as R squared. So R squared is just it's not something, it's not a value which is a squared value of something. It's just a particular value, right? It's just a value, and its notation is just an R squared. Okay, so there is no such kind of R, right? Okay, and then we have this R squared, which is our special kind of case, special kind of measure or statistic. And then if we take the square of it, and then we now have this absolute value of an R. So the conclusion is this correlation coefficient is almost the same as this R squared. And again, this R squared is the relative amount of the data that we can explain by using the linear regression line, okay, from the total amount of the variations in Y. Okay, so the total amount of information is the variance existing in our random variable Y. Okay. That's it for today. And so we have only a small part left, and then in this chapter I decided to skip a lot of parts. Okay, so these are not, these are out of our scope in this class. So then probably in the next class we will move on to chapter 10, which is our last chapter. Okay, thank you.